A very good day to my panel. My name is Alex Tiong Sie Hung with student ID AA16161. My FYP2 supervisor is Dr. Linka Singh, and my FYP2 research title is Final Element Analysis on Effect of Defect Length and Width upon Burst Capacity of Composite Repair Pipe. Moving on, next is my outline of my FYP2, and I come out with the first introduction, second literature review, third methodology, fourth result and discussion, and last the conclusion. Next, I'll start my FYP2 presentation with my introduction. Oil and gas pipeline or pipeline are globally used, and it is recognized as the most effective way, cost-saving, and safest way to transport the product. However, oil and gas pipelines are subjected to various deterioration, such as corrosion, which can lead to the occurrence of accident. For example, the rupture of oil and gas pipeline occurred and ensuing fire in the northern district of Marudin, Sarawak on January 13, 2020. 2 men were injured after a fire and explosion occurred early on Friday morning, 12th of April 2019 at an oil refinery being developed by Malaysian oil firm Petronas in Johor. A fiery blast ripped apart a section of Sabah Sarawak Interstate Gas Pipeline Project at the stretch between Lawas Town and Long Sukan in the northernmost district of Sarawak, resulting in the temporary shutdown of the 4 billion project owned by national oil giant Petronas occurred on 10th of June 2014. Thus, it is crucial for us in predicting the burst pressure of composite repair pipe and the lifetime of oil and gas pipeline. Next is my research background. Steel pipelines are susceptible to various deterioration, and there are 2 main repair methods, which is the first conventional method. However, conventional method is costly and dangerous. The second is fiber reinforced polymer composite repair method, and is more preferable by the industry nowadays as it is cheaper, lightweight, shorter repair time, and more effective. Next is my research problem. Oil and gas pipelines are subjected to deterioration, and there are 2 main costs in repairing it, which is the design cost and assessment cost. Design cost ASME PCC2 ISOTS 24817 show that the remaining strength of corroded area is dependent not only on material but also on the defect geometry. You can see in the equation that it encounters the thickness of the composite repair pipe. And next, the assessment code ASME B31G and the MVRP F101 also show that the thickness of the wall, the remaining wall thickness of composite repair pipe and the measured length of corrosion defect also encountered in the equation. Moving on next, there are 2 main objectives in my FYP2 research. With objective 1 is to investigate the effect of defect geometry on steel pipeline upon its burst capacity subjected to various defect width and length. And second, to determine the minimum and maximum burst pressure on different defect geometries and subsequently evaluate the influence of defect geometry towards burst capacity of composite repair pipeline. Next is my scope of study with the focus in predicting the failure of burst capacity of composite repair pipe subjected to various defect width and lengths. I use Abacus version 6.12 for my final element analysis. Next is my significance of research. My significance of research is to improve the repair system, but how? It's by considering the defect width and length into the repair system so that the design cost is less conservative and thus reduce the cost of pipe repair. Next is my literature review with link 2016 show that the existing design costs such as ISO and ASME only account minimum remaining wall thickness of defect pipe to design the minimum repair thickness. Neto Ferreira and Estefan 2015 show that the experiment done by Construction Steel Research 61 found that not only depth but also the length of defect geometry will affect the burst pressure of the pipeline. Hossam and Hawking 2014 found that for the burst intensity under internal pressure loading, the most critical longitudinal extent of a corroded region is the length variable. D1 at 2013 found that not only the depth but the shape of corrosion will also affect the performance of the pipe and increase the corrosion in the direction of the circumference of the pipe, reduce the axial load capacity. Chang at 2015 showed that the acceptable margin of error for burst pressure was 10% between the experimental test and numerical simulation, which were then used to do the validation of BESS model. Next is my methodology, and I divided into two stages, with stage 1 involving in the development of BESS model. The burst pressure of BESS model will be comparing with results from experiment tests. The marginal error will be not more than 10% when comparing the burst pressure of BESS model with experiment tests. If the result doesn't match, we will go back to the modification of finite element model. If the result match, which show that the marginal error of burst pressure is less than 10%, then it can be used as the BESS model or validation BESS model. If the BESS model is valid, then we'll go to the stage 2, which involves it in the parametric study. Then we will modify the validated BESS model with various of defect length and width and run the analysis to get the burst pressure result. Then I will evaluate the parametric study on the effect of defect width and length upon burst pressure of composite repair pipe. Next is my result and discussion. There are a total of 7 different combinations of defect length and width model created, with the smallest 42.1 millimeter defect length times 42.1 millimeter defect width, and with the largest burst pressure of 38.35 megapascal. And the largest combination of defect length and width is 420.8 millimeter defect of length times 420.8 defect of width, with the smallest to 26.57 megapascal. The results show that when the combination of defect length and width is getting larger, the burst pressure of the composite repair pipe is getting smaller. Next is my stress distribution contour of my finite element resist result, with stress distribution contour for the defect geometry of 420.8 millimeter times 420.8 millimeter composite repair pipeline show that the maximum stress distribution is 557.7 megapascal occur at the edge of the defect pipe. The middle picture shows that the stress distribution contour for the defect geometry of 420.8 millimeter times 420.8 millimeter of party. The largest stress distribution is 20.01 megapascal. The right corner picture shows the stress distribution contour of composite repair, composite red, with the largest 224.3 megapascal. Next, the bar chart representing the result of burst pressure of 7 different combination defect geometry of composite repair pipe. However, my analysis between the interval between each model is not consistent, so the result can be said it is not that accurate. So the bar chart below represent the burst pressure of different defect geometry or composite repair after adding the result finding from previous researchers there. So the interval between the model is consistent. Next, the finding. An equation of 0.0001 s squared minus 0.0895 s plus 41.115 was analyzed from this study, where it may help to optimize the existing design costs such as ISO and ASME that only account minimum remaining wall thickness of defect pipe into design the minimal repair thickness. The equation can be used in the future in estimating the burst pressure of composite repair pipe, and thus the work can be done much more effective. And the last is my conclusion. There are two main conclusions based on my two objectives. With conclusion based on my objective one, prove that when dimension of defect geometry in length and width defect increase, the burst pressure of the composite repair pipe has decreased. And conclusion based on objective 2, prove that the defect geometry with defect length times defect width 420.8 millimeter times 420.8 millimeter has the lowest burst pressure of 26.53 megapascal. This is the largest defect geometry. Next, it also proved that the defect geometry with defect length times defect width 42.1 millimeter times 42.1 millimeter has the highest burst pressure of 38.35 megapascal, which is the smallest defect of geometry. Next is the recommendation, is to investigate more combination of defect geometry so that the result of finding will be more accurate, and also conduct more laboratory tests on the combination of defect geometry used in this study to validate the result and gain more understanding. And last, the significance of research contribution. It can be a motivation for future research in optimizing the design of pipeline reliability system, especially in solving the problem of conservativeness in existing design costs. And that's all from me. Thank you.